Now our 9 suspects: Newton 0, Newton 1, symmetric 2, free P, Markov chain, free P50, free P10, inscrutable fate 1 and inscrutable fate 0 are all in place. I'm starting them off with equal prior probabilities, so it will be easier to see the effect of the data. This is possible because I have a finite number of models at hand. If I had an infinite number, then at some point the prior probabilities of the models should go downwards with increasing model complexity, because there's a lower limit to complexity but no upper, and the probabilities should sum to 1, much like the reset time earlier. So in such a setting, there's even prior concerns for keeping things simple. But in this finite case, we can have a flat probability. Now a quick reminder: the first and the last model, N0 and IF0, predict assured failure. The second, N1, predicts assured success. The rest starts off with 50% success probability, though only model 4 to 8 adapt to the data, and only model 4 to 7 changes the predictions based on these adaptations. So let's do the first trial. Turns out to be a success. Let's see what this means for the model probabilities. The first and last model are now completely out of the race already. Say goodbye to inscrutable fate 0. No! The second model, N1, predicted that this outcome had to happen, so it gained probability over the others, which predicted the outcome with the same probability as each other. Now model 4 to 7 adapts and changes their probability for the next trial to be a success. Model FP, FP50 and FP10 does this the same way, as for now they are the same model. The next trial turns out to be a failure, so it's time to say goodbye to N1 already. A shame, he looked like such a happy fellow. So both Newtonian-inspired models are out of the game. Not that this is evidence against Newtonian physics, it's just that its deterministic character isn't so interesting when the initial states aren't sufficiently determined. Model 4 to 8 adapts again, and model 4 to 7 again have their predictions altered. Let's hastily turn to the 10th trial. So far the models have jostled for positions without there being a clear winner. After this trial, model FP10 will separate from model FP50 and FP. For the next prediction, it reverts back to a 50% success probability. So let's skip to the 50th trial. Model FP10 is now nosediving out of the competition. Evidence is that what we've learned in each batch of 10 data is useful for predicting what happens in the next batch, at least so far as the 50th trial. FP and FP50 now has a clear lead, while the symmetric model S2 and IF1 seems to be ready for retirement. Evidently, the success probability is not exactly equal to 50%. The observed rate is 26%, and getting that rate with a success probability of 50% is improbable, compared to getting that result from the free binomial model. So we might as well say goodbye to S2, IF1 and FP10. I do continue to calculate on all of them, of course, but it now seems that only FP, FP50 and the Markov chain are serious contenders. Let's skip ahead to 200 trials. After 200 trials, which was all I had patience for, FP50 has also dropped out of the game, and the Markov chain model is starting to look very weak. The one-parameter model, FP, free success rate, is a clear winner. While it started with 1/9 of the probability, it has ended up so far with 83.62% probability. And that in competition with 3 easier models and 5 more complex ones. So we have evidence for repeatable independent trials with a fixed success rate, P. Without even specifying that we prefer a simple model if such is possible, we have still ended up with one, meaning that probabilistic reasoning contains Occam's razor. Or perhaps it's better to say that probabilistic reasoning specifies what exactly Occam's razor is and what it does. You don't want a model that is too simple to adapt and fit the incoming data, but you don't want one where fitting the data only confuses you about what happens next either. A model that is complicated enough to explain anything explains nothing, to paraphrase Daniel Dennett. What you want is something that is just right complexity-wise for understanding what you are studying, and probabilistic reasoning does that for you. One last thing, while inscrutable fate models didn't fare too well here, this doesn't rule out partially scrutable fate. However, going about creating models without any clear idea about how things can interact with other things means that you'll be casting about blindly for correlations. So you might end up with being afraid of black cats crossing the road and throwing salt over your shoulder for good luck. Slowly building up a worldview consisting of carefully studied physical interactions can help us reduce the complexity of the models we contemplate, and should thus give us a better tool for developing sound and useful ways to describe what happens in the world.